Hi, I'm Jaime Redondo. I'm a 14-year-old Spanish student, and I'm gonna talk a little bit about Möbius band and Klein's bottle. What is the Möbius band? It's just one of the most famous surfaces in mathematics. It has a lot of curious characteristics and properties, like it has only one boundary. But what is a Möbius band? How can you build it? Okay, you only have to take a string of paper, stick on one side, double it as if you wanna make a cylinder. But you have to double it once, a half twist, and you have a Möbius band. How can you prove that it has only one boundary? Okay, you can try to follow a line from, let's say, from here. I follow a line, and what you can see is that it has just passed it from the other side of the start point, and it's going for all the band without crossing it. It has go all the strip, crossing only at the end start point. This is a proof that it has only one bound. Okay, also we can say that it's a non-orientable surface. It's also because you can say what surface is here, so it's non-orientable. Also, we can define a characteristic like what happened if I cut the band. Okay, so let's just try. You start cutting. You can see I'm trying to go for the half side of the strip, approximately. It's difficult. Okay, so is that what you have? You have a longer and a stranger, a longer and a stranger Möbius strip. Okay, instead of having two pieces, you have one bigger. This is another property of this fantastic Möbius band. Also, we can set an operator, let's call it M, which means the half twist we do for create our Möbius band. So if we take another strip, we can see that if we make 0 half twist, what we have is a cylinder. If we do 1 half twist, you have just seen it before, we have a Möbius band. What happens if we do another half twist? We have another cylinder. And we can generalize that, saying that if we have a even number of half twists, even to n m, this is a numerical representation of an even number, we have always a cylinder. And if we make an odd number of half twists, let's say 1, 2, 3, 4, 5, what we will have, it's a Möbius band. Okay, we also can have a fantastic game. This is the game of the wells and houses problem. This says, Alice lives in house A. She must go for water to the wells 1, 2 and 3. Bob lives in house B. He also must go to the 3 wells. Caleb lives in house C, and he must do the same as Alice and Bob. Our goal is to draw the path between the 3 houses and wells without crossing the other paths. Okay, so let's just try. You have here Alice's house and the 3 wells. One, 2 and 3. Okay, so let's draw the path right here, here and here, for example. Okay, let's set Bob's house. Okay, his path is going to be here. Oh, he can't go here, it's crossing the path, so he has to go backward and back of Alice's house. Let's draw Caleb's house. He can go here to well number 3. He can go around here for well number 2. But how can he go to well number 1? Okay, so I just give you as a challenge that you can think in this problem. You can think maybe, I don't know, using Möbius band. Okay, so Möbius band also have a topological representation. It's not as difficult as it sounds. The topological representation of a cylinder is just this. What does it mean? These arrows and these straight lines. The arrows are in the same direction because you stick for making the cylinder without making any half twist. So for building a Möbius band, we have done a half twist. So one arrow may go to one side, but the other arrow must go to the other side. This is one way for representing the Möbius band. Also, calculus is very useful. So here in Möbius band, we also can find calculus. Here we find it as a way for representing the Möbius band. As you can see, it's a body in 3 dimensions. So we'll have 3 functions, which are the 3 coordinates x, y, and z. Okay, but what does it mean? There are 2 letters here. It's a function of 2 variables. It is just that we have a function varying in 2 variables. U, for the calculus presentation, we've taken that the Möbius band is the rotation of a line segment around a circle. We have twists, of course. We have that U is the angular position around the circle of the segment, and V is the position along the horizontal line. We also have another parameter in the function A, which is the radius of the circle about which the line is rotated. So we have here the function for x is A cosine of U plus V cosine of U halves times cosine of U. The function for y coordinate is just A sine of U plus V cosine of U halves times sine of U. And the z coordinate is AV sine of U halves.